Hi, everyone. I'm John Sanchez, and welcome to the DAC Pack, a series about all things direct air capture. In this video, we'll be talking about one of the two main models for performing direct air capture, and that is using liquid solvents. If you're curious about the other mechanism, using solid sorbents, check out the next video in the series. All right, so most of the figures and data from this video come from a paper published by the National Academy of Sciences in 2019. And that paper went into a lot of detail about the tech and the science behind direct air capture, but it was fairly technical. So my goal here is to take that paper and make it more accessible to you, even if you don't have a science background, and try to explain things along the way, while at the same time still going into a lot of the details and not and providing some intuition for why things are set up the way they are. So the context to keep in mind is that we're actually trying to pull CO2 directly from the atmosphere, from the ambient air when doing direct air capture. And this is particularly challenging because CO2 is so dilute in the atmosphere. At 414 parts per million, that means for every million air molecules, only about 400 of them are carbon dioxide. So this is an energy-intensive process. So the two main parts of any real air capture system are first an air contactor, whose job is to actually separate the CO2 from the air using a chemical called a capture agent. The capture agent will bind to the CO2 and thus therefore separate it out from the air. Then we have the regeneration facility, whose job is basically to decouple, unbind that CO2 from the capture agent so that we can reuse the capture agent to grab some more CO2, and therefore we don't have to keep adding more and more capture agent when we want to capture more CO2, and also to therefore have some concentrated CO2 that we therefore got from the capture agent that we can then either utilize for some product or sequester. So let's look at the overall process in much more detail. So it starts off here, like we said, at the air contactor, which takes in ambient air at, again, only 0.04% CO2, not much at all, and takes that CO2 gas and reacts it with our capture agent, potassium hydroxide, or KOH. That's going to keep coming back. So remember that this is what's ultimately going to react with the CO2 in order to capture it. This reaction produces two things: water, which we'll see is used in a later step, and K2CO3. The job of most of the rest of this air capture system is going to be to take the K2CO3 and do that regeneration. So get from it the CO2 and the KOH that we can then reutilize later. So we send the H2O and the K2CO3 into the next stage, which is the Causticizer. Here we take the K2CO3 and react it with another chemical, calcium hydroxide, CaOH2. Where do we get that? We'll come to that in a minute. And they react to form potassium hydroxide again, which is great. We've regenerated it. It can go back into the air contactor to capture more CO2. And it also produces the CaCO3. We'll get back to that in a second. But first, let's look at the CaOH2. We need to get this from somewhere. It doesn't come from nowhere. So we actually get it from this stage in the process, the slaker, which again produces CaOH2 by reacting the water, the H2O that we got from the air contactor. You can see the H2O being sent first from the air contactor to the Causticizer and then into the slaker, and reacting that water with CaO. Where do we get that? Well, you see, this is a big cycle, but ultimately this reaction creates CaOH2. So from here in the process, we have CaCO3 coming out of the Causticizer and CaO coming into the slaker. What has to happen to get from here to here? Well, notice that we're removing the C and two of the O's. CO2, we're literally removing the carbon dioxide from the CaCO3 to produce CaO, which is also known as quicklime. So in the rest of the process, we're literally just going to get that concentrated CO2 out, spit the CaO back into the slaker, and react it with water to get more of this CaOH2, which can react with the K2CO3 to regenerate the capture agent. It's a huge cycle and it's kind of confusing, but you just have to follow the flow of the arrows and it should make sense. So in this last step, we send the CaCO3 from the Causticizer into the clarifier and the filter press. This cleans it up a little bit, filters some waste out, and then also gets rid of some water. And then we send the CaCO3 into the most energy-intensive part of the process, which is called the calciner. The calciner has a hard job. It has to take this CaCO3 solid and basically heat it up to high enough temperatures so that it becomes this CaO, the solid that we're going to send into the slaker, and CO2. So the main workhorse of this whole reaction is heat. We actually need to heat this up to about 900 degrees Celsius for the reaction to proceed. That's huge. This is insanely energy intensive, and we'll talk more in detail about how that works in a second. But ultimately, this is the full system. The only other part of this diagram is the makeup. For example, for water, every year of this system generating, we probably need to add about 8 megatons or million tons of water to replenish the system. Okay, great. So that's at a high level what this is doing. We're now going to dive deep into what that National Academy of Sciences paper said about each one of these steps. But you should understand, at least by looking at this diagram now, what the cycle contains, how we regenerate that capture agent, and how we're capturing and ultimately releasing the CO2. If you have any questions about this process, especially after watching the rest of the video, feel free to leave a comment or let me know. Okay, so we're going to start in more detail on the air contactor. I have a lot of math and numbers here that are specifically from the paper, but what really matters here are the big ideas. So if we're assuming 1.5 meters per second air velocity, so this is the speed of the air, and we want to capture 75% of the CO2 in this ambient air, so the filtered air will only contain 25% of what was originally in there. We have some optimal geometries, so about 200 meters this way by 20 meters up and 8 meters depth is an optimal geometry as determined by the paper and a previous paper that it was based on by Jeff Holmes and David Keith of Carbon Engineering. So given that we need about, if we want to capture 1 million tons or 1 megaton of CO2 per year, we need about 38,000 meters squared of cross-sectional area this way. To do that, that means we need about 10 of these contactors to achieve that, just doing simple division. Then we're going to pack the inside of this air contactor using this plastic polymer called PVC. It's packing material. This is the specific model, but ultimately the goal is to put packing material all throughout here and distribute the KOH, that capture agent, throughout the packing material. The issue is that when we send air or any gas through solid area, that will create this pressure drop where as the gas moves through this solid, it's going to lose pressure. And that's an issue because we needed to maintain that pressure. And in order to do that, we're going to have all of these fans literally providing the pressure for that gas to move through this packing material. So one question we inevitably have to answer is how much energy are those fans going to need in order to run? How much fan power is required to drive sufficient air through the contactor? So these calculations are from the paper and sort of work through that. But essentially, we're calculating the pressure drop based specifically on this Brentwood packing material. And you can calculate it using this formula where D is the depth that you need to move the air through and V is the velocity that the air is moving with. And doing the calculation for a depth, here we said 8 meters for depth. So from 6 to 8 meters, we get these pressure values in pascals, and plugging them into this formula, which takes the pressure drop that we just calculated and also the volumetric flow rate. So that just means how much volume we want to push through here per second, how much air volume we want to push through here per second, as well as how efficient the fans are, which we can assume to be about 60%. We get power of about 10 megawatts to 37 megawatts. And then the last step here of this calculation, which I know is long and the details don't really matter, is doing some basic dimensional analysis to reach the conclusion that in gigajoules or billion joules, we need about 0.315 or 1.17 gigajoules per ton of CO2 that we want to capture. That might sound like a lot, but ultimately, in the scheme of things, you're going to see it's not too much in terms of the overall process. Once we get up to that calciner, you'll really see the energy required racking up. From some final things we want to talk about the air contactor include how much water the system is going to lose. This is affected by a few things, including how concentrated the KOH is in the initial solution of the contactor. The relative humidity around there might absorb water. But at any rate, this is that makeup box in the initial diagram where we're going to need to add about 8.2 megatons per year of water if we want to capture 1 megaton of CO2 per year. And then finally, we need some pump in order to get that KOH across the packing material throughout the whole contactor. So to pump this KOH evenly across the packing material, the rule of thumb that Holmes and Keith proposed in their initial paper was that you need about 15% of the fan energy in order to do this. So taking 15% of these numbers here, we get 0.048 to 0.065 gigajoules per ton of CO2. So that's the air contactor. That was a lot of math. That'll be dialed down from here on, but hopefully you get some perspective on where these numbers actually came from if you were curious, and also some of the different factors involved in building an air contactor. So then we're going to move down here to the slaker. Remember, the slaker's goal was to take the CaO, which just had CO2 removed from it in the calciner, react it with water from the air contactor, and then produce the CaOH2, which is needed for this regeneration process in the Causticizer. So this is actually an extremely favorable reaction. The delta G here, you'll see that in every box. Delta G basically is a measure of how favorable the reaction is thermodynamically. And if it's negative, that means it's very favorable, or it is favorable. So here we have a negative 27.7. So that sort of suggests that we don't need very much energy input, and indeed only 0.005 gigajoules per ton required. Not very much. But some issues with the slaker are that we might produce inert grit, so like solid waste products that might accumulate and impact efficiency for the worst. The other thing that we'll get back to is it's an exothermic process. That's this delta H, which means that the reaction releases heat. We don't have to input heat in. In fact, when the reaction proceeds, it releases heat. So we might ask the question, if we need heat for a lot of parts of this process, can we utilize that heat that's released somehow in a later stage in the process? And the answer is it's kind of difficult to capture and reintegrate, but we'll actually talk about one possible way in a few slides. But moving on to the Causticizer here. Again, the Causticizer took the K2CO3 that was produced from the reaction in the air contactor and reacted it with the CaOH2 from the Causticizer to regenerate the KOH and produce the CaCO3. So this is also, like, looking at this delta G, it's also a very large negative value. Like it says here, it's pretty negligible in terms of the work for the causticization reaction itself. The reason that we have 0.109 gigajoules per ton for the causticizer is actually for this clarification step, where we have to remove small amounts of the fine particulate solids that might be here in the CaCO3, which was in that clarification step. But the energy intensive step here is actually the heating and drying, which comes because we need to remove the water content of the CaCO3 before we really heat it up to that 900 C in the calciner. So we don't want to be heating, we don't want to be expending energy to remove that water there. So we want to do it first. And so it's actually going to require 3.18 gigajoules, which, comparing that to the rest of these numbers, is fairly significant. It's an energy intensive process to remove that water and dry it. So it's certainly something to consider. All right, so yeah, we've sent it through the clarifier and the filter press, and now we're moving into the calciner, whose goal is to heat up the CaCO3 solid to produce CaO, which we'll send into the slaker, and also the CO2, which then we can sequester or utilize. So again, this is requiring heating to an extremely high temperature, about 900 C. This is a large thermal requirement. So one thing I haven't been pointing out along the way is I also have CO2 generated here. So what are the emissions of each step when we produce this energy? And it'll depend on how we produce that energy. If we're using a natural gas or a coal plant, obviously coal is going to emit more CO2 than natural gas. But in either case, you see the emissions values here in terms of megatons again per year. But looking through these numbers, the oxy-fired calciner, especially for the coal, like 0.57 to 0.85 megatons per year is pretty substantial compared to the rest of these numbers. So that's something to keep in mind. So the idea is perhaps when we're generating all of this heat, we can co-capture the CO2 that's produced, meaning when we emit CO2 out of the exhaust pipes from this plant that's producing this energy, maybe we capture that CO2 as well and then can sequester or utilize it as we wish. The issue there is that If you're just combusting regularly using, the air, which is mostly nitrogen, then what's going to come out and be captured isn't going to be mainly CO2. So we need to use what's called an oxy-fired kiln. So rather than combust our natural gas or our coal with regular air, we want to exclusively use O2 or oxygen, so that we end up with concentrated CO2, a concentrated CO2 stream produced with some water, which we can filter out. So that's why we have this air separation unit here, which is going to separate out the oxygen from the air that we can then use to produce the heat for the calciner, which then can have CO2 emissions that can be co-captured. So the air separation unit also requires some energy input, but not too substantial compared to the calciner itself, only 0.30 gigajoules. And then the last thing here is there's an opportunity for heat recovery, which we were talking about on the slaker slide here, where it's an exothermic process. So maybe once this very hot CaO from the calciner reaches the slaker and releases some heat as well in that reaction, maybe we can capture that. So one opportunity is the drying of CaCO3 here in the clarifier that we talked about on the last slide, this heating and drying step. That can perhaps be set up with steam that's released from this lime hydration, this adding water to the quicklime, the CaO, in the slaker. So using this heat recovery process, or perhaps we can offset 2.39 gigajoules per ton of CO2 from that drying step. So subtracting from here. That's most of the process. In terms of the makeup, just walking through the things that we'll need to replenish. So we talked about the water loss in the air contactor, but we might also need to replenish some KOH, which could be lost through formation of aerosols and spray drift. So that would be 400 tons per year. And then another big thing in that air contactor is insects, birds, particulate matter, sulfur oxide. So a bunch of gunk basically might enter the air contactor and accumulate, and it'll combine with the calcium. So there's calcium in a lot of the steps. So from the slaker, the CaCO3, the CaOH2, the CaO. So we might need to replenish some of this calcium because the calcium ions might combine with some of the things that enter the air contactor. So one solution, and deemed the best solution, is adding some CaOH2, about 3,500 tons per year, to account for this loss, mostly because of the calcium products that we could add to keep going in the cycle. This one's low cost and has a pretty low carbon footprint. So looking at final totals now, we've been through the entire system. We know how all the stages work and which are particularly energy intensive. We can actually break down the energy requirements into two categories. A lot of them listed here are electricity requirements, so powering the fans and the pumps and the slaker and the Causticizer and the clarifier and the air separation unit. So all of those things require electricity inputs. So that actually only accounts for 6 to 18% of the actual energy we need to input. The rest of it, which is the bulk, is the thermal requirement, so actually producing heat. And this heat, we need it for the heater and dryer, and then obviously for the calciner. So this is much more significant. And as I said, there's debate in the literature about how much heat we can actually recover at different stages from exothermic processes or from an exchange of heat after coming out of the calciner, because it's difficult to integrate. So there's some debate about what's possible. But ultimately, we see the overall mechanism, and looking at the final process. Again, just with the bigger picture in mind, we need to capture CO2. So this system, it's liquid solvent. Our liquid solvent is KOH, potassium hydroxide. This is our capture agent. And that's going to produce K2CO3, which then the whole point of the rest of this whole system, the regeneration facility, is to have that K2CO3 release the KOH and ultimately release the CO2 so that the cycle can continue. I hope that makes sense. If you have any questions, or if there's any direct air capture content you're looking for, please leave a comment. I'm happy to hear from you. And remember, we're at 414 ppm CO2 already and only counting. So let's get to work. See you soon.